Good morning, everyone. Thanks for joining us this morning in this webinar on Modbus Variable Conversion Enhanced IEC. The presentation itself is just over the 15-minute mark, so we'll go into that and then we can take any questions at the end. But if you do have any questions, feel free to put them in at any point during the presentation.
Hello and welcome to today's webinar. Today we're going to be looking at Modbus Variable Conversion in Enhanced IEC 61131. Let's get started. Let's look at our agenda for today. We'll start with a quick Modbus review. We'll look at the traditional way that Modbus has been implemented in the Horner controllers. Then we'll compare standard IEC versus enhanced IEC and the way things are handled a bit differently with those two approaches. And then we're going to get to the Modbus implementation for enhanced IEC. We will finish with a Q&A session. Modbus is the most common industrial protocol for linking devices from various manufacturers. There are two prevalent variations. Modbus RTU is a serial protocol over RS-485 and Modbus TCP is an Ethernet protocol over Ethernet. Modbus RTU follows a master-slave configuration, while Modbus TCP is client-server. Modbus has a data model designed around traditional PLCs from the past, focusing on Boolean and integer data types. It features digital inputs, digital outputs, and analog inputs stored in 16-bit variables. The addressing scheme includes 1-bit and 5-digit variables with 10,000 registers per register type, allowing for a total of 40,000 registers. The 6-digit scheme is less common. Traditionally, Horner has implemented Modbus in its product using a variable map that aligns Modbus data types with Horner data types. The original OCS was designed with a similar architecture to the traditional PLC model, featuring 16-bit registers and 1-bit Boolean type addresses. While the address types are a bit different, the standard map has been widely used and proven effective for various programming styles within Horner controllers. Now we'll look at the difference between standard IEC and enhanced IEC in the Horner controllers. The standard runtime engine, present in almost all OCS controllers, supports variable-based advanced ladder, register-based advanced ladder, and standard IEC languages. These languages can be executed from the standard Horner runtime logic engine. However, for the XL series, XL Prime series, and the upcoming Canvas series, there's an additional option to execute enhanced IEC. This is made possible by a special enhanced IEC runtime logic engine included in those products. Now we'll look at the technical details. The three original languages, register-based advanced ladder, variable-based advanced ladder, and standard IEC, all execute from the Horner runtime engine. However, the standard IEC requires a code conversion in Cscape before download, as it can't run directly on the Horner logic engine. On the other hand, the enhanced IEC can run directly from the enhanced IEC runtime logic engine. This direct connection results in faster execution times and a larger capacity, as there's no conversion needed. With enhanced IEC, there are no traditional underlying registers like %or, M, or T. Thus, the standard memory map between Horner and Modbus won't work. Instead, int and bool array variables are created and used for Modbus data. In our configuration for Modbus TCP, We select whether to configure Modbus server or Modbus slave. Then we allocate 4 arrays: holding registers, input bits, and coils. These arrays allow seamless exchange of Modbus data for integer and Boolean types. Now we'll look at non-integer data types. Traditionally, manufacturers have exchanged floating point data, double integer data, and more through Modbus, which is based on integer data. In the register-based, variable-based, and standard IEC editors from Horner, there was a conventional register-based structure for easy concatenation of 16-bit registers into real and floating point data. However, with Enhanced IEC, this shortcut isn't available. Moreover, Enhanced IEC enforces strict variable type matching, making it impossible to mix integer and real data with the same function blocks. Therefore, we must adopt a different approach. When it comes to Enhanced IEC, the solution is quite simple. At Horner, we've created user-defined function blocks to handle double integer and real variables effortlessly. You can easily split them into separate integers for Modbus transmission, or join separate integers to create double integers or floating points. These user-defined function blocks take care of the complex logic behind the scenes, so all you need to do is use them. On the screen, you'll find the first 4 UDFBs for splitting and joining double integers, both signed and unsigned, and the same approach is available for floating points. It's a straightforward process with these UDFBs. Now we'll consider a real-world application involving a machine with an encoder. The encoder provides a 32-bit value that we store locally in the OCS as a double integer. However, when the SCADA package retrieves this value through Modbus, it can only handle single integers. This is where our user-defined function blocks come in handy to handle the conversation for seamless communication with the SCADA system. However, when it's going to be retrieved through Modbus by the SCADA package, Modbus really only supports single integers. So what will we do here? We're going to use one of those user-defined function blocks so that we can split that double integer variable into separate integer components so that it can be seamlessly read by the SCADA package. The Modbus TCP server configuration in the OCS allocates 4 arrays for the Modbus data types. The encoder is to be mapped at the start of the Modbus input registers. For example, Modbus addresses 30,001 and 30,002. In the OCS, using our user-defined function block, we'll split the 32-bit double integer into 2 16-bit variables. Store the broken down data in Modbus input registers, Modbus input register 0 and Modbus input register 1, making it accessible over Modbus. In our program, we use a single function block to split the encoder position, which is a double integer signed variable. The output of this UDFB gives us 2 integers. We allocate one to index 0 for Modbus input registers and the other to index 1 for the same array. It's quite straightforward. In the same application, we may have the SCADA package writing a position target or set point that needs to be monitored in the OCS. This data is coming in over Modbus and will be written into 2 separate integer locations. Now this time, because it's being written to the OCS, it's going to be stored in holding registers instead of input registers. Input registers are read-only, holding registers are read-write, and again we're going to allocate those 40,001 and 40,002. So that means again that they're coming in through that input array, and then we're going to use the join UDFB to take those two different integers and combine them into a single double integer. Now we'll have a demonstration to see how we accomplish this. We'll start in Cscape. Here's our program, which is doing exactly what we talked about on the slides. We'll start from the configuration. So if we go into the hardware configuration and we go into the LAN 1 configuration and then to the Modbus slave configuration, here's where we see the 4 different arrays that we have allocated to Modbus data for holding registers, input registers, coils, and inputs. Now these arrays were created using the variable window, and depending on the size of those arrays, Cscape will automatically allocate the size for each of those different Modbus data types. So we've only allocated 4 holding registers, 4 input registers, 4 coils, and 6 inputs. And that's based on the dimension of those arrays that we've created. They can be much larger than that, but that's what we've used for this example. So now that we have those Modbus addresses configured, we have these 2 UDFBs that we're using. One of them is used to take our encoder position, which is a double integer, and split it into integer components that are mapped into Modbus input registers. And the other one takes the 2 inputs that are being written by the SCADA package into the holding register area and combines those to create the target position. So now we'll look at the bench. Firstly, we'll look at the encoder position. So the encoder position is representing the position of the encoder, and that is a double integer value. And we made this just editable from the screen for demonstration purposes. And then our UDFB splits those into 2 different components at addresses 30,001 and 30,002, where they can be read by the SCADA package and then reassembled on the other side. So, to simulate our SCADA package, we're using Modbus Pull. So now we'll go back to the computer and Cscape, and this time we'll bring Modbus Pull to the front. We've set our encoder position at 67,000, and it's being displayed here as you can see in Modbus Pull, and we're going to change that to 69,000. So, as you can see, we have successfully configured Modbus Pull to interpret the integer data that we're sending over Modbus as a double integer value. And then, going back the other direction, we have target position. So that comes in as 2 separate integers, and then we're reassembling it here. So we've assembled it as 660,000. If we go back and take a look at how it's being sent from the SCADA simulation, we can see it's 660,000. And then we modify it here to be 665,000 and we press send. So when we go back to the bench, we can see that we successfully assembled that data properly. So by using these really simple user-defined function blocks, we've been able to take something which otherwise could be quite complicated and make it straightforward. Now we'll look at how you import user-defined function blocks into Enhanced IEC. So we go to the project navigator. Under Logic Modules, we right-click and say Import Logic Module, and then we navigate to the folder that contains the user-defined function block files. Now one thing that is a bit different is the file extension for IEC user-defined function blocks is XK5, whereas the file extension for variable-based advanced ladder is CPU. But effectively, once you have found the UDFB that you want to import, you simply select the file, press open, and then it will be added under UDFB modules over here in the project navigator. Once it's imported into your project, it's very simple to add to your logic. You need to go to the section of the logic where you want to add it, and then you go over to the project toolbox. And at the very bottom under project, you'll find when you expand that all of the user-defined function blocks have been added to the project. So the one that we just added can be added to the project simply by dragging it off to the location of the logic where we want to add it. And like all user-defined function blocks, they do need naming because they're each a unique instance of the other. So that is very important, of course, because it allows you to have multiples of the same UDFB just working on different variables and different Modbus data in your program. So that's how you add a UDFB to your project in Enhanced IEC. In conclusion, Modbus is widely used in industry and supports 16-bit integers and 1-bit booleans as its native data types. However, there's often a need to transmit other data types like double integers or floating points over this protocol. While traditional Horner languages can easily concatenate integer values into 32-bit data types using built-in %or memory, Enhanced IEC lacks this feature. But we have simplified the process by creating user-defined function blocks for easy splitting and joining of data types. That concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, hopefully that was of use to you. And if anyone requires a demo program with this, we do have one available, so just get in touch with tech support and we can get that out to you. Okay, so next week our webinar is on system registers that are not used as often. So the registration is there available for that, and again we have more webinars ready to go up until the end of August, so you can register for those now as well. Other than that, thank you all for joining this morning, and we hope to see you again next week. Have a good day.